During your calculus course, you might have seen something called a line integral of a vector field over a curve in the plane. If a curve is closed and non-intersecting, there is a theorem that you can use to transform the line integral of the vector field to a double integral over a region and vice versa. This theorem is called Green's theorem. However, to be able to do this, we must have a planar simple closed curve which has a positive orientation. In this video, we will give the definition of the positive orientation of a planar simple closed curve and how you can determine this. Let us start with some stuff we need in this video. Consider this planar simple closed curve. We denote a closed curve in the plane by the letter C. The plane region inside of the closed curve C is called D. The plane region D consists of all points inside and on the closed curve C. We will also need the parametric equations of a closed curve, which are in general of this form. Now we have the things we need. We can directly give the definition of the positive orientation of a planar simple closed curve. A simple closed curve C has a positive orientation if increasing the parameter t from A to B results in a counterclockwise traversal over the closed curve C. If the traversal over C is clockwise, the curve C has a negative orientation. So how can we determine whether or not we have a counterclockwise traversal? Time for some examples. Let us start with the easiest simple closed curve there is, a perfect unit circle, which we will call C1. The plane region inside the circle we call D1. This circle C1 has, for example, the parametric equations x is equal to cosine of t and y is the sine of t, where the angle t is between 0 and 2 times pi radians. If we take t equal to 0, we are in the orange point 1, 0. If we then increase the angle t, we move along the circle C1 in a counterclockwise direction, which we can indicate with some small arrows on the circle. Because we have made a counterclockwise traversal over the circle, this closed curve C1 has a positive orientation. We could, however, also take a different set of parametric equations to describe a circle. For example, this one. If we take u equal to 0, we start in the point 1, 0. Increasing u gives that we now traverse the circle in a clockwise direction, which we again can indicate with some small arrows on the circle. In this case, we have made a clockwise traversal over the curve C2, so with the alternative parametric equations for a circle, we have found a negative orientation of C2. So we must conclude that the parametric equations of a curve define whether a curve has a positive or negative orientation. But how can you determine if the closed curve has a harder shape than a circle? Well, for this we can take a close look at the two circles. Think of standing at 1, 0, the starting point. If you are walking counterclockwise over the circle C1 on the left, the plane region D1 is always on your left. If you, however, envision yourselves walking clockwise over the circle C2 on the right, the plane region D2 is always on your right. This observation is true in general, so we can state it as a theorem. A simple closed curve C has a positive orientation if the enclosed region D is always on the left as you traverse along the curve C. Now we have an easy way to determine the orientation of a closed curve. Let us do an example together. Here you can see the racing track at Zandvoort in the Netherlands. On this track, the racing drivers drive normally in one direction only. As the racing track is a simple closed curve, we could say the orientation of the curve is defined by the driving direction during a race. Here you can see a map of the circuit. The start and finish is in the bottom, and the small red arrow indicates the driving direction. We can add some more red arrows to show the driving direction more clearly. If we follow the red arrows, we see that the inside of the track is always to our right, so the track has a negative orientation. Now you know how to find the orientation of a simple closed curve in the plane. Consider a simple closed curve in 3 dimensions. Can such a curve also have a positive orientation? How would you define that? In another video, we will tell you.